My name is Yahel, and I'm a PhD student at the Astronomical Instrumentation Group under the supervision of Dr. Sagi Ben-Ami. And today I'm here to present you a unique instrument that I had the opportunity to design and build during my master and my PhD here at the Institute. And this instrument, we gave him a name. The name is HiSpec, and it is a high-resolution spectrograph that was designed for the study of white dwarf stars. So let's start from the beginning. What are white dwarfs? The story starts with a star like our own sun. And we all know that our sun has an internal energy supply in its core. Nuclear fusion, converting hydrogen atom into helium atoms. But one day, in the future, in about 5 billion years from now, our sun will simply exhaust all its nuclear fuel in its core. And then our sun will expand and will transform and evolve into what we call a red giant. Now, how giant are red giants? Let's put it into scale. If I will plot Earth's orbit as our ladder, and this is the size of our sun today relative to Earth's orbit, as you can see, as a red giant, our sun is going to grow so much that it might reach Earth's orbit and may even engulf us. But don't worry, it's only in about 5 billion years from now, so it is okay. And then after a relatively short time that the star will spend as a red giant, the star will shade its outer layers, and the core of the star will construct and become what we call a white dwarf. Now, if we will put it again into scale and assume that this is the size of our sun today, this is going to be the size of our sun as a white dwarf, extremely small. Now, if we look at the population of stars in our galaxy, we will learn that more than 97% of the stars will go through this evolutionary path and end their life as white dwarfs. And because of that, I don't need to convince you why it is interesting. If we want to understand the universe, we need to understand white dwarfs. In astrophysics, I don't know if you ever thought about it, but we do not control the experiment. I cannot grow a galaxy in lab, feed it with some dark matter, put some hydrogen atom on top, and then choose a white dwarf, cut it to two, see what's going on inside. The only thing we can do is look up and make observations. And the reason we can see stars, we can detect stars, is because stars have temperature. And because of that, they emit thermal radiation. And the brightness, the absolute brightness of a star will be a function of the temperature of the star and the size of the star. And I just told you that white dwarfs are extremely small. Our sun as a white dwarf is going to have the radius about of the radius of our Earth today. And because of that, this is a challenge for us to study white dwarfs because they are very faint. Comparing the brightness of our sun today, the brightness of our sun as a white dwarf will be 4 orders of magnitude fainter. Now let's go a step back and talk about observational astrophysics. How do we make observations? The simplest tool that we have as astronomers is taking a picture. In order to do it, we need a telescope and a detector in the end. But if I'm interested in a specific white dwarf here in the picture, the amount of information that I can retrieve from an image is very limited. And because of that, the next tool that we as astronomers usually do is to measure the spectrum of the star. By measuring the spectrum, what we do is measure the flux, the number of photons, as a function of wavelengths, or function of the energy of the photon. And I don't need to convince you that the amount of information that we can see, that we can retrieve from the spectrum of the star is enormous compared to the amount of information we have in a single picture. And in order to make this observation, in order to measure the spectrum, what we need is a telescope and a spectrograph. Now let's talk about white dwarf spectrum. We already said that white dwarfs are extremely small. But also, if we compare the mass of our sun today to the mass of our sun as a white dwarf, it will be comparable. which means that these objects are extremely small, extremely dense. They are so dense that it is like taking 5 tons and put it in a teaspoon. And if we compare the average density of our sun today to the average density of our sun as a white dwarf, it is by million times denser, 6 orders of magnitude. And because of that, the signature, the spectroscopic signature of white dwarfs is very unique and differ from regular star. Assume that this is the spectrum of a regular star. This is a simulation, and all the lines that you see, it's not a noise, it's a feature. This is a real simulation of a spectrum of a star like our own sun. And on top now, you can see the expected spectrum, the simulated spectrum of a DA white dwarf with exactly the same temperature. And what you can see that we have only a set of few very broad and unique in shape absorption line, and most of the information is concentrated in only few spectral bands. And although you're already all convinced that white dwarfs are very important for us and we want to study them better, and although they are very faint, very hard to observe, and has very unique spectroscopic signature, till today, there was not even one instrument that was specifically designed in order to measure the spectrum of white dwarfs. But let's go another step back. What does it mean to optimize an instrument for a specific science case? What do we need to do? So in every instrument, there is a set of trade-off relations between the different parameters of the instrument. If we are talking about spectroscopy in astronomy, the most inherent and basic relation is between resolution and the signal-to-noise that we will have. If we will have higher resolution, we will have more information, but the amount of photons that we have in each resolution element is going to be lower. And for spectrographs in astronomy, we also need to add other parameters. For example, the band coverage. Will it be infrared or UV or visible? Will it be a wide band instrument or a narrow band instrument? The dispersion method, will we disperse it with a prism, with a diffraction grating, with a more sophisticated technique? What is the optical design? Is it a reflective design or refractive design? Will we have internal obscuration? Do we correct only geometrical aberration or also chromatic aberrations? What is the sensitivity of the instrument, the complexity of the instrument, the simultaneous coverage that we will have, the image quality which will dictate the resolution that we will have in the end, the instrument efficiency which will dictate the number of stars that we will be able to observe, the cost of different components, and also the telescope size, which in a not trivial way will also influence the final resolution we will have in the instrument. And when we started designing high spec, we had the freedom to tune all the different parameters that we had in the system. And it was clear for us that an instrument that is designed and optimized for white dwarf study is an instrument that will prioritize efficiency over bandpass. And we decided that high spec will cover a set of, will deliver high resolution, but will observe only few very, very narrow spectral bands, and will retrieve all the information from these bands. And the exact resolution and the exact bands will be dictated from the science that we want to do with high spec. Now, unfortunately, I don't have a lot of time to talk about all the science that we plan to do, but we can split it very roughly into 3 categories. Questions that relate to the past of the white dwarf, which is actually the future of our own Earth. What is the fate of planetary system? Will our Earth survive this transition? And also, I just told you about a mechanism in nature that breaks planets into pieces. Can we use it and search for signatures that will help us to understand the composition of planets outside of our solar system? Questions that relate to the present of the white dwarf are interested in understanding better the mass distribution of white dwarf in order to solve some discrepancy that we have that relate to the mass distribution as function of temperature of white dwarf and cooling ages. And also one very important question that relates to the future of white dwarf. And what we hope is to be able to help answering the question, does a merger of double white dwarf is indeed the source of the most powerful explosions that we see in the universe, type 1a supernova? And with all of that in mind, we were able to construct, to tune the other parameters of our system. What is the exact resolution that we need? Not too much, not too low. And what are the exact bands that we need? That we will have only the information that we need and nothing more, because we want to keep it as efficient as possible. And we started with a sketch design, and we tuned also all the other physical parameters of our instrument. We had a mechanical design, and we sent all the different components into production and slowly got them back. We assembled the instrument in lab. We were able to produce a light of a fake star in order to measure it with high spec. We measure the image quality that we get with the instrument, and finally today we are able to measure the fake star light in all the relevant bands that high spec can cover and solve the wavelength solution for all of them. I will mention that with high spec we expect to be able to observe in high resolution more than 7,500 white dwarf, which is an order of magnitude more than the current largest survey of white dwarfs in high resolution, which is very exciting. And I can't finish my talk without mentioning the telescope itself. The telescope itself that high-spec is going to be coupled to. We call it MAST, the Multi-Aperture Spectroscopic Telescope. It's a very unique telescope. It is actually not an individual telescope. It is an array of 20 telescopes. And in the end of each telescope, instead of having a detector or a spectrograph, what we have is an optical fiber that collects the light, and with a set of 20 optical fibers, we collect the light from all the 20 telescopes, and all these fibers go into our instrument room where high-spec is waiting on the optical table. And I will also say that it is not only a plan, this is actually a video from last week, and today the team just went again to Neot Smadar, to our new observatory, to commission the first 2 telescopes in the array. And we plan to be on sky and start measuring a white dwarf spectrum by the end of this year. That's it. Thank you.